So in the previous lecture, I had done a sort of revision of the concepts up to kinetic theory of gases to give you a guidance lecture for the upcoming test. Having done that, in today's lecture, we will again continue forward. But what we'll be discussing in today's lecture will not be coming in on Sunday's test. Sunday's test is going to be major test 7, that is, it's going to be in heat and thermodynamics only up to the applications of kinetic theory of gases directly. So make sure you're clear about that. Okay. Right, so let's look at the statement of first law of thermodynamics again. So it says that for an ideal gas, the total heat supplied or the net heat supplied to the gas is equal to the change in the gas's internal energy plus the work done by the gas. And W is equal to the work done by the gas. Okay, so last week when we were looking at this relation and its applications, we had seen that delta U is equal to NF by 2R delta T. And it is therefore what we call a state function. That is, it is independent of path. But W, which is integration of PdV, or that is the area under the pressure volume graph, it is what we call a path function. Or it is path dependent. And therefore Q this also becomes a path function because it's the sum of a path and a state function. So obviously it becomes path dependent. Okay, so if we are describing any particular thermodynamic process by a PV graph, where this is the initial state, let's say, and this is the final state, and there is some kind of a path from the initial to the final state. The area under the P versus V graph. That's the work done by the gas. Okay, so far, as you can see, we have two particular formulae. One is a direct formula which gives us the value of delta U, independent of whatever the path be or whatever type of process is happening. As long as we know the initial state and the final state. Remember, the state of a gas is given by its parameters, pressure, volume, and temperature, and by the equation of state PV equal to nRT. So as long as we know the initial state and the final state, we can calculate delta U directly. F, remember, is the degrees of freedom. Whereas to calculate the work done by the gas, we need to know not only the initial and final state, but we need to know the equation of the path going from initial to final, so that we can solve this integral or we can calculate this area. So this is what we have looked at the last time we were at first law of thermodynamics. Okay. Now let's continue that further today with applications of first law. In the applications, we will look at the four standard processes. That is isochoric, isobaric, isothermal, and adiabatic. We'll look at these in detail and develop equations and formulae for each of these. So as we look at these processes, we will look at the processes or we'll understand the standard processes in two contexts. One is in terms of the experimental setup, and the other is the PV graph. So in the experimental setup, what we will typically have is a heat insulated container with a movable piston, and on the piston we have a load to control the pressure. And we have some kind of also a heat through which we can supply heat or absorb heat from the gas. Both of them is possible. And we have n moles of an ideal gas. With degrees of freedom F. So this is our typical experimental setup. Whereas PV graph, you know already, any state change is represented by a curve. So this is the general thing. Now we'll apply it specifically to these four standard type of processes. Now, one very important point over here, the application of first law, that is Q is equal to delta U plus W, and equation of state, that is PV equal to nRT, will be done here for any process assuming the gas has isotropic pressure and temperature during the process. That means during the process, the gas has uniform pressure at every point inside and uniform temperature at every point inside. So that implies that the process has to be very slow, or this type of slow process is called quasi-static process. Quasi-static means almost at rest. Shall I explain more about quasi-static process? Just note down this concept up to here first. Okay, so what this process, this concept of quasi-static process basically means is that during the process, as the graphs of or as the state of the graph is moving from one point to another in the PV curve, each intermediate state is a well-defined state in which PV is equal to nRT. So every point is like an almost static equilibrium point. So quasi-static means a very slow process such that in the path from initial to final state, every intermediate state is almost static. Hence the term quasi-static. This is the meaning of the term quasi-static. Okay, so next let's understand the application of this to the first of our four standard processes, which is isochoric process. Okay, sure. Yeah, I'm scrolling back up. Finish writing this down. Okay. Durgesh, you are also done? Okay. Yeah, so as I was saying, let's come to the first of our named processes or standard processes, isochoric process. So the definition of an isochoric process is a process at constant volume. So the experimental setup will look like this. Instead of the piston, now it is a fixed volume container in which we have our ideal gas. Let's say the volume of the container is V naught, and through the heating element, we can supply or withdraw heat to control the temperature of the gas. So the PV graph of the same now will look like a horizontal line because, sorry, like a vertical line because volume is constant. Not a horizontal, it will look like a vertical line because the volume coordinate should remain constant. Could be like this, or it could also be in the opposite direction. Okay, now the first thing is from equation of state, okay, so that's the first thing. Pressure is proportional to temperature because the volume is constant, and work done, which is integration P dV, is zero because volume is constant. That is area under PV graph is equal to zero because it's a vertical line, as you can see. So because pressure is proportional to temperature, what it also shows you that in the above graphs, temperature at B is greater than temperature at A, because pressure at B is higher than pressure at A. Therefore, A to B in the first graph is an isochoric heating because the temperature is being increased, whereas B to A in the second graph is an isochoric cooling. There's the second graph. This one is the first graph. So we have to visualize this experimentally in such a way that suppose we are supplying heat very slowly through the heating element from the initial point A. So it's going from A to the next point above A and reaching a new equilibrium where pressure and temperature have increased slightly, volume has remained same. Then we are supplying a bit more heat, so it's going a bit more up. So from point to point, it goes from equilibrium state to equilibrium state very slowly from A to B. Similarly, if the element is such that we are absorbing heat from instead of supplying heat, starting from the point B, let's say. So very slowly is going from B to the point just below B, where the pressure and temperature are slightly less than B. And it's a new equilibrium, then to the point below it, then to the point below it. So every point is like a new equilibrium state. So at every point, the equation of state is valid, that PV is equal to nRT. That is how we understand the quasi-static process. Okay, now next thing, we'll see that W was 0, that we've seen, because okay, but delta U is NF by 2 R RT. Okay, finish writing that part. Okay, so the second one becomes our definition of change in internal energy. The first one we already seen, the definition of the work done, that is 0. Yeah. So now note down this delta U formula. So remember, delta U is a state function. So it doesn't matter whether it's isobaric, isochoric, whatever. This formula that we have, this is a state function. So this formula is universal for all processes. So it's path independent. So once we are seeing that W is 0, Q becomes equal to delta U, because W is equal to 0 in an isochoric process. Okay. So Q is given a special term over here. Q is N into CV into delta T, where N is number of moles, of course, but CV is molar specific heat capacity It is molar specific heat capacity at constant volume, or what we call isochoric. Molar specific heat capacity. So we'll look at a word definition of it also, but first note this down. So substituting this in the above formula, that Q is equal to delta U, see NCV delta T is equal to NF by 2R delta T, which gives us the formula for CV. It is F by 2R. So the molar specific heat capacity at constant volume is equal to F by 2 times R, or CV is equal to 3 by 2 R for monoatomic gases. And CV is equal to 5 by 2 R for diatomic gases. So CV is the heat supplied per mole per degree change in temperature. During an isochoric process. Hence the name molar specific heat capacity at constant volume, or isochoric molar specific heat capacity. Okay, so this is the complete description of the thermodynamic process in terms of first law as well as equation of state. So let's look at a quick question. A sample of hydrogen gas at initial pressure 1 atmosphere, volume 2 liters, and temperature 300 Kelvin is heated isochorically to a final state at final temperature of 400 Kelvin. So find final pressure and final volume. Find the change in internal energy, work done, and heat supplied. Okay, just try out this question. Yes, very good. That's correct. Srishti, your answer is correct. Okay. See, when you're doing a question like this, what is expected is that you should understand that isochoric का मतलब क्या है. The definition of isochoric is constant volume. So from that you understand that pressure will be proportional to temperature and volume is constant. So P final upon P initial will be the ratio of the final to initial temperature. So 1.33 or 4 by 3 atmospheres. Correct, Dhruv, that's correct. Good. So Prachi, you've given the value of Q, acha, in terms of R, but should it be in joules or liter atmosphere or what, like that? You have to understand that also. Okay. So the final state will be 1.33 atmosphere, 2 liters, 400 Kelvin. Whereas the initial state was 1 atmosphere, 300 Kelvin, 2 liters. Okay. So that's as far as the equation of state goes. Okay. Now delta U will be equal to Q, will be equal to NCV delta T or NF by 2R delta T. So Q is equal to delta U and work done will be 0. Okay. That's the definition for isochoric process. So this can be written as F by 2 into final pressure minus initial pressure into the volume. So 5 by 2 because it is hydrogen gas, so diatomic. Okay. So final pressure we saw is 4 by 3. Initial pressure was 1 atmosphere. So that's 10 raised power 5 approximately pascals. Into the volume was 2 liters. So that is 2 into 10 raised power minus 3 meter cube. So this is how we can directly calculate it in joules. So 5 by 3 into 10 raised power 2. That is approximately with a positive sign. So heat is supplied and internal energy increases because it's an isochoric heating. Okay. So remember this conversion, 1 atmosphere is approximately 10 raised power 5 pascals and 1 liter is equal to 10 raised power minus 3 meter cube, and 1 pascal meter cube is equal to 1 joule. Okay, okay. Right, we can also calculate it in terms of R. Okay, but then we'll have to calculate number of moles and all that. Na? So Okay, so all this is understood. And now the final thing, the graph, as you can see, the temperature is increasing. So it will be isochorically, the temperature is increasing. So it will be a vertical straight line. So the PV graph, if we are drawing, that will be like this, going from an initial state of a pressure of 10 raised power 5 pascals to a final state at a pressure of so much. Okay. So the temperature is like this and the volume is 2 liters. So that is the detailed PV graph. Okay, next let's move on to the definition of our second standard process, which is an isobaric process. So an isobaric process is one in which the gas is undergoing a thermodynamic process at constant pressure. Quasi-static thermodynamic process, or very slow. So experimentally, how we conduct this is that our container has to have a free piston which is kept with a fixed amount of loading on it. So I'll explain what I mean by that. So suppose the mass of the piston is negligible and the area of cross section is A, then the gas inside is at a fixed pressure of atmospheric pressure plus mg by A. Okay. Because if you look at the free body diagram of the piston, you'll understand that the piston is experiencing three forces. The normal contact force that the block is applying on it equal to its weight. the gas from inside is applying a force of pressure into area, and atmospheric air from above is applying a force of, and this is in equilibrium. Okay. So that is what shows us that the pressure of the gas is equal to P naught plus mg by A. So as long as we keep the mass of the load constant, the pressure of the gas inside will remain this fixed value. Okay. So now while keeping that fixed value, if we supply heat very slowly, okay, then what will happen is that the moment we have supplied a bit of heat, the pressure will tend to increase. Okay, but the piston will move up to balance, to adjust the volume in such a way that again the final pressure comes back to this. Or if we withdraw a bit of heat, the pressure will tend to decrease. But the moment that happens, the piston will come down because it won't be in equilibrium anymore. It will come down to the new equilibrium pressure point where again the pressure balances. So supplying or withdrawing heat slowly through this heating element will result in the pressure, the volume of gas or the position of the piston self-adjusting such that the equilibrium of the piston always remains intact. That is, the pressure of the gas always remains P naught plus mg by A. So that is how we practically achieve a slow or quasi-static isobaric process. Okay. So isobaric expansion would look like this on the PV graph. At some constant pressure P, the volume is increasing from V1 to V2. Whereas isobaric compression just look like the reverse. The volume is decreasing from V2 to V1 while the pressure is constant. So this is the experimental explanation as well as the graphical analysis of isobaric process. Just make a note of this quickly. Then we will see the formula related from the first law. Yeah, A is the area of the piston. That's correct. Over here. Okay, so now let's see the equation of state and first law of thermodynamics used in this. So the formula for work done, which is the path function, becomes like this. You can also understand this from area under the graph. Okay. Delta U is the same. Okay. Q here becomes what we call NCP delta T, where Cp is isobaric molar specific heat capacity. Okay. Or molar specific heat capacity at constant pressure. So next, when we put together these formulae in the first law of thermodynamics, we will understand the value of Cp for an ideal gas. Okay, so now substituting these values in the first law, we get the formula that Cp is equal to F by 2R plus R, or Cp is equal to Cv plus R. So this is an important formula. So for monoatomic gases, the value of Cp is 5 by 2R, and for diatomic gases, the value of Cp is 7 by 2R. Okay, so that is all about isobaric processes. Now next, let's move on to the third type of standard process, which is isothermal. So this is defined. So you want to note down? Okay, finish that. Okay, so let's come to isothermal process next. So an isothermal process, as you know, is a thermodynamic process at constant pressure. Constant temperature. So the visualization of this process is very simple. We can just put the gas in a container which is made of conducting walls, heat conducting walls. With a free piston with a variable load in it. So whatever is the temperature outside, the gaseous temperature inside will remain fixed because the walls are conducting. So if the load is increased slowly, the gas will compress, maintaining its temperature. So it will tend to heat up as it compresses, but heat will flow out through the conducting walls, maintaining its temperature constant. Similarly, if the load is decreased slowly, the gas will expand, but this time heat conducts into the gas, maintaining constant temperature. So that is the experimental setup for isothermal process. So temperature is constant means that pressure is inversely proportional to volume. So our PV graph looks like a rectangular hyperbola, inverse proportionality. So we want to compress the gas isothermally. You have to very slowly add mass on the load for the piston. So very gradually we keep on adding mass onto that load, and very gradually the gas will compress, and every time it compresses a bit of heat will come out to maintain the constant temperature. Similarly, if we want to expand it very slowly, then very slowly we have to remove mass from the piston, from the load on the piston. And every time it expands a bit, it will tend to cool down, but heat will conduct through the walls and maintain the temperature constant. Yeah, heat conducts into means that it conducts into the this thing into the chamber from outside. The direction of heat conduction is from the outside into the gas. Yeah, for one step processes, we cannot draw a graph like this because there is no intermediate state between initial state and final state. And therefore, our equation for work done will not be correct, that it is integration of P dV, because P is, I mean, we cannot predict the curve through which. So, so what happens is that if we have a sudden process, the load affects the pressure, na beta. We understood the pressure of the gas inside is equal to P naught plus mg by A, na. See, the pressure at which the gas is existing is atmospheric pressure plus mg by E. So by increasing m, pressure is increased. By decreasing the mass, pressure is being decreased for the gas. Understood, na, Samarth? So that is first and foremost something important. Okay. Yeah. Now coming back to Prachi, your point that if it is not a quasi-static process, now like it's suddenly if we add a lot of mass instead of adding mass slowly, then the piston makes a sudden compression. So during that sudden compression, no, the gas will not be in an isotropic state, where the temperature is constant throughout the gas, where the pressure is same at all points inside. So it is in an unpredictable state. So we cannot plot the graph on the PV curve. So any of the path functions like work done, Q, etc., cannot be calculated. So for sudden changes, we cannot calculate any path dependent quantity like work done and Q, etc. Okay, so the while the statement of first law is okay that Q is equal to delta U plus W, but none of the formulae that we are developing over here will be applicable because these formulae are for the specific processes which are happening through the specific curves, the well-defined specific curves. So hence basically our application of the first law of thermodynamics is subject to the special condition. It's like, you can say that we are dealing with ideal type of processes which are quasi-static. Whereas for non-ideal processes, the experimental results will not really agree with the formulae we are developing. Okay, so next up, let us understand work done, which is integration P dV. So this will become this kind of an integration. Yeah, exactly. These are laboratory processes only, and they have to be conducted very slowly, like I've explained. So if we are compressing the gas isothermally like we're doing here, then the walls of the container should be made of conducting material like metal or something instead of insulator, and the load should be added very, very slowly. Should not add the load very fast. Hence we have the diagram where we have variable mass where we are adding, let's say, something like we are adding something like sand or lead pellets or something onto this loading piston, and we are adding it little bit of mass at a time, not a whole lot of mass at a time, so that the change is very slow. Or if we are removing mass to make the gas expand, we are removing it very slowly in very small steps of mass removed per in intervals of time. Okay, so that is the whole purpose of quasi-static process. So anyway, in this integration, nRT naught is constant, so we have that logarithmic integration. You know that integration of dx by x is ln x plus c. So integration of dx by x from x equal to a to x equal to b becomes ln b minus ln a, which becomes natural log of b by a. So we are using this result here. So this is the work done by the gas. This is the formula for work done. So you can see that if V final is greater than V initial, then ln V final by V initial will be positive. So work done will be positive because it is an expansion. Whereas if it is the other opposite way around, it is a compression. So work done will come out to be negative because this will be a negative quantity. Okay. Now next up, let's understand that delta U will be 0 because change in temperature is 0, and delta U in general is defined as nf by 2r delta T as a state function. So in isothermal process, what is happening? Logically also, isothermal process, the temperature is constant. Therefore, the kinetic energy of gas molecules remains constant. So internal energy is constant. It does not change. So basically what happens is that any heat exchange results in mechanical work. So Q is equal to W is a positive quantity when heat is supplied and work is done by the gas during an isothermal expansion. Whereas Q will be equal to W will be a negative quantity when heat is absorbed from the gas. So Q is negative. and work is done on the gas. W is negative. During an isothermal compression. Just make a note of this, people. Okay, so the formula for Q is equal to the same thing, nRT natural log of final upon initial, whereas W is 0. Sorry, delta U is 0. So these are the three terms of the first law of thermodynamics application. So just make a note of this, then we'll look at an example. Okay, people. So hope this formula is clear. Now let's look at a quick application example. So a sample of oxygen gas at a pressure of 1 atmosphere, volume of, or let's say the pressure initially is 4 atmospheres, the volume is 2 liters, and temperature of 300 kelvins is isothermally expanded to a volume of V2 equal to 5 liters. And then isobarically compressed back to a volume of 2 liters. Okay. So first of all, plot the PV graph for the two successive processes. Secondly, calculate Q, delta U and W for isothermal expansion, and calculate Q, delta U and W for the isobaric compression. Okay. Again, take 1 atmosphere to be 10 raised to 5 pascals. Also find the final state of the gas. The final volume is 2 liters, but what about the pressure and temperature? So you see that as long as you have your basics correct, that you understand the type of graphs involved, okay, and you also understand how to apply equation of state and each of the terms of the first law. These type of questions are very easy. They are almost formula based. Just try this out, people. I'll put it up in a moment. Yeah, in the same graph only, you have to plot in succession what is happening. So let's understand. One after the other, two processes are happening. So we'll just plot them in succession. So from our initial state, which is a pressure of, let's say, P1 and a volume of V1 at a temperature T1, okay, we are having an isothermal expansion to a volume of 5 liters. So it's going like this. Hyperbolic curve. So this is our first process. Okay. So we can see that P1 V1 will be equal to P2 V2 isothermal. So we can also see that this final pressure will be 2 by 5 into initial pressure. So it will be 1.6 atmospheres. Okay. And then the second process from here is going to be an isobaric compress back to the volume of 2 liters. So the isobaric compression will look like this. Okay, so now let's calculate for each of the processes. Yeah, so I'm working that out. So for the isothermal process, okay, delta U is 0 and Q is equal to W is equal to nRT, natural log of final by initial volume. Okay, so that is nothing but nR into 300 into natural log of 5 by 2. Okay. Now notice that P1 V1 is equal to nR T1. So nR into 300 is equal to 4 into 10 raised power 5 multiplied by 2 into 10 raised power minus 3. So nR into 300 can be replaced with 800 joules. So this is 800 ln 5 by 2. Okay. So Q is equal to W is equal to this much. And delta U is 0 for the isothermal process. Aditya, you're giving the answers for the isobaric process? Yeah, so then that's not correct, no? Because Q and W are positive in the expansion. So just refer to my calculation. I've given it all here. Now in the isobaric compression, it's quite easy. Okay. Now P delta V will be the pressure which was P2 into V1 minus V2. So P delta V and W are negative quantity. So this final pressure P2 we had seen is 1.6 atmospheres. This initial pressure was this much. So it is 1.6 into 10 raised power 5 into 2 minus 5 into 10 raised power minus 3. So it is minus of 1.6 into 3 to 10 raised power 2 joules. So work done is minus 480 joules. Q is minus of F by 2 plus 1 into 480 joules. And delta U is minus F by 2 into 480 joules. Now, since I'm not given which type of gas it is, we'll just leave it in terms of F. But if it is monoatomic, F will be substituted as 3. If it is diatomic, F will be substituted as 5. Like that. So here in the question, I have not mentioned which gas it is. So we'll have to leave the answer this way. Achha, it's oxygen gas. Okay, so then we will substitute F as 5. It's oxygen gas. Okay, anyway, so hope you understood this question, all of you. Okay, so we will conclude today's lecture here, and next time we will pick it up from here and discuss about adiabatic processes and then more applications of first law. But once again, this is not coming in Sunday's test. First law of thermodynamics applications you don't need to prepare. You just need to prepare up to kinetic theory of gases that we discussed in the last lecture. Okay? So that's it for today's session, people. Wish you all the best.